We're going to look at our homework over the weekend, worksheet number 22. We had 5 questions that we want to go over, 4, 5, 8, 9, 10. We'll start with number 4 here. It says a cathode ray passes undeflected through an electric field strength of this value and a magnetic field strength of this value. What's the speed of the cathode ray? We know there's 3 sections in the cathode ray tube, right? There's what I call the acceleration chamber, where the charged particles speed up. There's just an electric field there, and the charged particles speed up. The acceleration chamber, chamber number 1. And then we have the velocity selection chamber, where some of the particles get deflected upwards, some get deflected downwards, but some end up going straight through undeflected because Fe equals Fm. And in the third chamber, once we've gotten rid of that electric field and we have just a magnetic field, the charged particle just goes in a circle. So of course we say Fc is equal to Fm. So it's going to be one of these 3 chambers here, the acceleration chamber, the velocity selection chamber, or the main chamber. As Thomson did, all 3 of these chambers to find, what did he find, by the way? Thomson calculated what? Not the charge, the charge to mass ratio. And he found that charge to mass ratio was really, really big, which meant the mass was really, really small, in fact, smaller than the mass of any atom, which means that the particles were subatomic, right? Negatively charged subatomic particles, hence the discovery of the electron. All right, which chamber of the cathode ray tube do we have here in question number 4? Cathode ray tube, or cathode ray, which is, we know a cathode ray is a beam of electrons, right? It passes undeflected. Bruce, what do we got here? Good, that's the velocity selection chamber. And in the velocity selection chamber, we set Fe equal to Fm. There is one more thing besides the undeflected part of it that tells me it's the velocity selection chamber. What is that other thing? Yep. Good, you have both an electric and a magnetic field. All right, so this is what we got here. Chamber number 2, or the velocity selection chamber, Fe is equal to Fm, or Qe is equal to QVB. Q's cancel. Left with E is equal to V times B, or I can rearrange that and solve for V, I get E over B. Now I got my numbers, just sub them in and solve it fairly easily at this point. E is 6.00 times 10 to the 3. We could say volts per meter here, as we give you in this question, but we could also say newtons per coulomb. Both of those are valid units for electric field. B, the magnetic field strength, is 6.50 times 10 to the minus 3 Tesla. When I do the math there, I end up getting 9.23 times 10 to the 5 meters per second. And that seems like a pretty reasonable speed, right? We usually expect to see something times 10 to the 5, maybe 10 to the 6 meters per second. Could be a little faster, could be a little slower, but this is pretty typical, at least. All right. All right, let's take a look at question number 5 now. This one says, a cathode ray passes undeflected through an electric field and a magnetic field. What's the kinetic energy of the cathode ray? Okay, this is an interesting question. What's the kinetic energy of the cathode ray? Well, this is similar to the question that we just did, right? Except instead of looking for speed, we're looking for kinetic energy. This is a velocity selection chamber. If the last one was, then this one is too. So let's say for this one, Fe equals Fm. Let's say QE equals QVB, the electric force equals the magnetic force, and we'll solve for V here. We get the value of E and B. We solve for V there. We end up getting a speed of 714.285.7 meters per second. But I'm not done with that. What do I got to do now? If I want to find kinetic energy, then I'm going to say Ek is equal to 1 FmV squared. Good. But what's the mass? We're not given the mass of this cathode ray here. Thomson wouldn't have known what the mass of a cathode ray is, but we do. Does that mean we're smarter than Thomson? I don't know. We know what the mass is anyways. What is the mass of a cathode ray? What is a cathode ray? Yeah, it's a beam of electrons. So we're going to use the mass of an electron. 9.11 times 10 to the minus 31 times the speed squared. And when we do that, we get Ek of 2.32 times 10 to the, I think it's negative 19. Is it negative 19? And of course, the units for that would be joules. Is that all right? Next question we want to go over is number 8. It says a cathode ray passes undeflected through an electric field and a magnetic field of this, and then it enters just a magnetic field. What's the radius of the path followed by the cathode ray? I just copied and pasted my information from my 3 chambers or 3 sections, the acceleration chamber, the velocity selection chamber, the main chamber. Which one am I going to do here? The main chamber, okay. So let's identify that, the main chamber. We have FC equals FM. Okay, that's, like if we're looking for a radius, it's got to be the main chamber, right? Because it's not going in a circle anywhere else. So we'll say mv squared over r equals qvb. V's cancel. I'm left with mv over r equals q times b. And I'm looking for the radius. So let's say r is equal to mv over q times b. It's a cathode ray. I know the mass, right? It's 9.11, mass of an electron. Q I know. B I know. What's the value of v? What's the value of the speed? Don't know. So what do you want to do? Logan, what do you want to do here to find speed? Well, I can't rearrange because we're looking for r too, right? We don't know what r is. We don't know what v is. We've got to find v some other way. How did Thomson find v? Martin? Yeah, using the velocity selection chamber. Good. So we'll say Fe equals Fm. QE equals QVB. Notice when I do these, I derive them each time, only because they don't appear on my data sheet. So I don't want to have to memorize a special form of an equation. I want to be able to figure it out since it doesn't appear on my data sheet. Okay, if I try to memorize everything, then I'm going to mess up on probably everything. So be able to figure it out. You don't have to clutter up your brain with, oh, was that E over B or was that B over E? Right? Like, if you're like me, there's only so much space up there, and there's pretty much full. It's pretty much full up there now. It's like, well, just figure it out then, as opposed to trying to memorize it and clutter up my brain even more. The electric field here is, what is it, 6,000? 6 times 10 to the 3. The magnetic field is 7 times 10 to the minus 3. That gives us 600,000, 6.0 times 10 to the 5. Okay, there's my speed. Now I take that back, plug it into here, knowing that m and q are the charge and mass of the electrons, of the electron. We end up getting 6.83 times 10 to the minus 4 meters. How many people ended up getting that? If you look at this part of the question, it's not that hard. If you look at this part of the question, it's not that hard. But somehow it seems like when we put them together, it becomes harder. Don't make it harder. Don't let it beat you. Okay? Don't let this question beat you by putting 2 things together. Sorry, typo here. Or what do you call it when it's handwriting? Handwriting O? Okay, handwriting O here. I was looking at question number 9. The numbers going in there are correct, but the value of the speed is wrong. It's 8,57142. That goes into here, and that gives me 6.97 times 10 to the negative 6. Martin, is that right?
I don't think I got that.
Yes? Okay, good. Okay, let's take a look at number 9 now. It says electrons in the CRT are accelerated through an electric field of this value, magnetic field of this value. Electric field is removed, leaving only a magnetic field. What's the radius of the electron's path? This is almost the same question, but in this one, it says we have an electric and a magnetic field undeflected. So that's a velocity selection chamber, right? But then we remove an electric field. Like, picture this. In question number 8, we had this. The charged particles went straight through here and then entered this chamber and bent like this. That was question number 8. Okay, question number 9, we have this. Charged particles are going through undeflected here, and then what happens? They get partway through, and then we take away the electric field. So then what happens? This. It's the same thing, right? It's not going from one section to the next, or from the velocity selection chamber to the main chamber. Rather, the velocity selection chamber is becoming the main chamber, right? We're still going to analyze it in exactly the same way. We're going to say for the main chamber, we're going to say FC equals FM, because that's what we got when we start this question. MV squared over R equals QVB. R is equal to MV over QB. Great. We know what M is, we know what Q is, we know what B is, don't know what V is. Well, what's V? We'll solve for V when we had a velocity selection chamber before we took away the electric field, where we say FE equals FM. QE is equal to QVB, or E is equal to E over B. Here, when we solve for the speed, this time we get 6.00 times 10 to the 5 meters per second, which will turn around and sub back into here and end up getting a radius of the path, this time of 6.83 times 10 to the negative 4 meters. So don't make this question harder than it has to be. It's the same question as number 8. It's just worded a little bit differently. It's set up a little bit differently. But in the end, you're the end user here. Okay, the end user does exactly the same thing as we do in question number 8. Doesn't matter how we get there. Okay, it doesn't matter whether we have a main chamber and a velocity selection chamber because it goes from one to the other, or one becomes the other. It ends up, for you, the end user, being exactly the same thing. And finally, question number 10. Number 10 says, electrons in a cathode ray tube are accelerated from rest to a potential difference of 1300. They enter a magnetic field of this. What's the maximum radius of the electron's path? Which section or sections of the cathode ray tube are we dealing with in this question? I heard somebody say, yeah. Okay, the acceleration chamber, because it's accelerated from rest to a potential difference of this value. Then what? That's not it. Because in the acceleration chamber, it's not going in a circle, so there is no radius in the acceleration chamber. Quinn, what do we got after the acceleration chamber here? Good, the main chamber. So let's do EI equals EF for the first one. What kind of energy do we start with if they start from rest? Dawson, what energy do they start with if they're starting from rest? Good. Potential. It's not MGH potential though, right? It's QV potential. Good. What kind of energy do they end with? Shaylin, what kind of energy do they end with here? Yeah. Once they speed up, they've got kinetic energy. Now, when we solve for VF here, let's sub in our numbers and get it, and then I'll ask that question. 1.6 times 1300, bless you, equals 1/2 of 9.11 times 10 to the minus 31 times VF. VF there works out to be 213, I think. Is that right? Okay, that's my VF. And then I'm going to do the whole FC equals FM thing for the main chamber. As Shaylin told me here, FC equals FM. mv squared over r equals qvb. V's cancel. R is equal to mv over qb. And I have the value of v here, right? Sub into here. M is the mass of the electron. Q is the charge of the electron. Got the value of B. Solve for R works out to be 4.87 times 10 to the minus 3. Now, question. Why is it in this question that I'm asking you not for the radius of the electron's path, but rather the maximum radius of the electron's path? Did anybody catch that little wording there? Yeah, maybe that messed you up, actually. If I had asked for radius, maybe you would have been a little bit more successful at it. Thomas, why am I asking you for the maximum radius, not just radius?
Is it because you find the maximum kinetic energy?
I didn't find kinetic energy here. Yep.
It's because there's no magnetic field and electric field, so it's not just the maximum speed, it's the maximum speed as well as other speeds.
Okay, good, good. Yeah, so as the charged particle speeds up, some of them are going to be going that fast. 2.1, right? But some of them might not be going quite that fast. We're not dealing with a velocity selection chamber here, so we're not filtering out all but one of the speeds. We're not just taking one of the speeds and allowing them to go into the main chamber. As far as we know here, we're allowing all of them to go in. So they're all going to end up with different radii. Well, the ones that are going to be moving the fastest, which are these particles right here, they're going to have the biggest radius. So when I solve for R here, using the maximum possible speed, some of them could be going slow, right? But using the maximum possible speed, then I'm going to get not necessarily the radius of all of them, but the radius of the ones that are moving the maximum possible speed. So you can see here why Thomson, we wouldn't want to do QV equals 1/2 mv squared if we're doing Thomson's analysis here for a couple of reasons. One, as we said, because Thomson didn't know what Q and M were, right? He didn't know what the values were. That was the whole point. And the second thing was that, well, they weren't all moving that fast. Only some of them were moving that fast. He needed to know not the maximum possible speed, but rather the exact speed that they were moving. Now let's have a look at practice question set number 27. Question number 1. Experiments with cathode ray tubes led to the discovery of the... Yeah, man, like you get a question like this on your exam, you got to get this. Like you got to get this. Okay? If you don't study, well, then you might miss it. But this is a question that, like, you know you're going to get hard questions on the exam, right? And there's probably going to be a few questions that even those of us that work the hardest and are the smartest, like, there's probably going to be 1 or 2 questions that even those of us who are those people aren't going to get. Right? Like hard questions. That's okay. But if we're not going to get some of those hard questions, we got to get the easy ones. And this is an easy one. It is the electron. 2, the property of cathode rays that provides the best evidence to suggest that they are not electromagnetic radiation is that what? What's the answer to this one? This one's not a crazy hard question, but it's a little bit harder than the first question. Blake, what do you say for this one? How do you know that they're not EMR? How did Thomson determine that they were negatively charged particles? Not subatomic, but just negatively charged. C. Yeah, they can be deflected by magnetic fields. Now, how did he determine that they were subatomic negatively charged particles? Well, the idea of the charge-to-mass ratio, right? It was so big that the mass had to be so small that they had to be subatomic. An experiment is designed to study the charge-to-mass ratio of hydrogen ions. This isn't really a cathode ray tube, right, if we're dealing with hydrogen ions. Because hydrogen ions are not just individual electrons. They're all moving in the same direction, the same speed. Mass spectrometer, which is essentially the same thing as a cathode ray tube, except it uses ions instead of electrons. What's the radius? Well, this would be FC equals FM thing, right? We'd rearrange it. We'd sub in mv squared over r equals qvb, and then we'd rearrange it to solve for r, and I get mv over qb, and my answer is B. Four, graph that shows the relationship between radius and the strength of the magnetic field is which one? I don't know. Off the top of my head, I don't know. How do I tackle this? How do I tackle this graphical relationship that I've never been asked before? Sorry? Yeah, write down an equation, which is, in this one, is going to be one you have to derive, but it's one that we've derived a number of times. Fc equals Fm. mv squared over r equals qvb. We want to solve for r, because it's on the y-axis. Okay, it's the same equation that we derived in the last one. What's the relationship between r and b? Right, what graph does that give me? A, B, C, or D? R is inversely related to the magnetic field. As magnetic field goes up, radius goes down, and vice versa. Which one is it? A, B, C, D? D. Yeah, it's D. Like A and B are both showing B going up, R goes up. C, I could see you picking that, because as B goes up, R is going down. But when we have a 1 over x or 1 over x squared, either one of those will give us a shape that looks like D. Those shapes would be slightly different, but you wouldn't be able to distinguish them, but just by looking at them, they would look the same. Okay, so 1 over x or 1 over x squared is going to give me D. You're never going to get one that's C. Okay, you'll never get one in Physics 30 that's C. Oh, here's a good one. Manipulated variable in this experiment is modified in order to obtain a straight line graph as shown below. Hey, do you see why 1 over b on the x-axis gives you a straight line? Because it was a 1 over b relationship, right? So when you look at this, like basically we say y is equal to mx plus b, right? Well, y is r, and m is slope, and x is 1 over b. Well, so that gives me my relationship. Y equals mx plus b now gives me my relationship. R is inversely related to b. Now, I don't know what they're asking for here. Let's see. Which of the following expressions gives the correct value for the charge to mass ratio? Oh, okay, good one. Which of the following expressions gives the correct value for the charge to mass ratio? We got to go through that process, don't we? B, by the way, disappears, right? You can see clearly that it goes through the origin here. R is equal to mv over qb. We should derive that, but we just derived it twice for the last two questions, right? It's the same equation. R is equal to mv over qb. Cross off things that appear in both. What am I left with? Slope is equal to mv over q. So what does that boil down to? What are we looking for here? Okay, so we're looking for charge to mass ratio. So we're going to have to rearrange this to solve for Q over M. Q goes up, M goes down. Slope goes down. Is that right? Q goes up, M goes down, slope goes down. V over the slope, I think that's right. Speed divided by slope, so my answer would be C. How many people got that one? 5. Okay. It's a harder one. It's a harder one. But like we got to expect this, right? Like this is coming, right? We know for sure this is coming. We are going to get a question, at least one question on your exam that's a graph that you've probably never seen before, just like this one, and that you're going to have to deal with. Figure out what the slope represents and do something with that. Man, there's lots of questions on this. Worked your heart over the weekend. To determine the speed of the charge to mass ratios, or the speed of the charged particles in the cathode ray tube, Thomson balanced the forces produced by, this would be electric and magnetic field, right? The velocity selection chamber. And 7, I think, is the last one, isn't it? An alpha particle passes without deflection, electric and magnetic fields. It's the speed of the alpha particle. So it's not a cathode ray tube. It would be like a mass spectrometer, but we can deal with it the same way. Undeflected would be the velocity selection chamber. Fe equals Fm. And we want to find the speed here. So we say V is equal to E over B, right? Sub our numbers in, right? Well, we can't because we don't know what E is. Maddie, how do you find E there, the electric field? Anybody else? What is it? No, well, we could rearrange that, say B times V, but we don't know what speed is, right? So then you're kind of going to go around in circles, right? We need another equation here to help us to find the electric field. Other Maddie. Maddie's going to help let Maddie off the hook here. Yeah, it's delta V over delta D, the electric field between parallel plates. I know it's been a little while since we've done that, right? Unit 2. The potential difference between the plates is 300 volts. The distance is 0.040 meters. Should have circled that. I'm not sure what we get there, but when we get it, whatever it is, we sub it back into here, and we solve for the speed. What did it work out to be? I'm going to guess C or D. What is it? D. Why did I guess C or D? And that was a bit of a guess, but... Sorry? Yeah, 10 to the 5 is pretty typical for charged particles. Is 10 to the 3 possible? Absolutely it is. Absolutely. 10 to the 5 is more common, though. So if I was going to guess, I would guess 10 to the 5, not 10 to the 3. Doesn't mean that 10 to the 3 is wrong. Just in this case, it is, of course.